So this is chapter 4, section 4, optimization. And like I said in my video that you guys watched, optimization is just finding the maximum or minimum. And there are two ways you know how to find a maximum or minimum. First of all, you know they occur at critical points or endpoints. So one way is to find the critical points, find the endpoints, and then find the actual value of the function you're trying to maximize or minimize and see which one's biggest. And obviously that's the maximum. The new one you have is if you have only one relative extrema, then it's actually an absolute extrema on a continuous function. It must be continuous. So those are the two ways that we're going to use to find absolute max and min. Okay, so this garden problem. First, find what you're trying to maximize or minimize. We want to minimize the combined area. The combined area is the garden and the sides around it, the grass border. So we want the minimum area. Now, why would you want to minimize that? Because you want to take the least amount of space, right? But also notice they want the garden to be a specific size. The actual flower garden, this inside part, they want to be 30 square meters. So that part's set. Now, looking at this picture, this here is also 2 meters, and this here is also 1 meter. So how are we going to arrange this to maximize? They want the dimensions of the whole garden. So I need to define some variables, and this is where some of you don't like. You have to actually make up some variables. You have to make some decisions which you're not used to doing and you don't like doing. And so the only way to get better at this is just to try. And you have two choices. You could either call this distance here X. I chose X. You could have called it A, B, C, D, Q, Z, whatever you want. Or you could choose to call this whole side to be X. Now, it's kind of your choice. And it doesn't matter. In the end, it comes out the same. Sometimes one way is easier than the other. I'm going to choose the inside to be X. Now, here's the other thing I need to know. I'm going to call this Y. Now, you could have chosen this to be Y. You could have, and that's not wrong. So there's more than one way to do this, and that's why some of you don't like these, because it's kind of open-ended in some ways. You get to choose. And honestly, sometimes one way makes life easier. So it's kind of random and through experience. So we want the dimensions of the combined area to be minimum, okay? Minimum combined area. So since we're trying to minimize area, we need a formula for area. But the area of the whole thing. So now, how far is it from here to here? You should see that's X plus 4. Because you have X and then 2 more on each side, so it's X plus 4. And then you ask yourself, what's the distance from here to here? That's going to be Y plus 2. Why? Because this is Y, and you have 1 more on each side, so it's Y plus 2. So now we have the area of the whole thing is going to be base times height, X plus 4 times Y plus 2. That is what we're trying to minimize. So we need to find the critical points of that. So therefore, we need to find the derivative. But we have another problem. We have 2 different variables, and that's no bueno. We have to eliminate one. So somewhere else, there's got to be more information where we get another equation that relates those 2 variables together. And here it is. You were told the area of the inside is 30 square meters, right? So you're going to use all the information. Everything else we've already used. All that's been used here. The only unused is the 30 square meters is the area of the inside. Well, what is the area of the inside? Base times height. So we're going to do base times height equals 30. That's the area of the inside. So now we have another equation, xy equals 30. And you have a choice again. You can either choose to solve for y or to solve for x. It doesn't matter. You get to choose. So what do I like better? I'm going to solve for y. I don't know why, but that's what I'm going to do. Divide both sides by x. Now you have a value for y that you can use to put in here. And why would we do that? Because if we do that, we don't have y's, we only have x's in our equation, and that's mucho bettero. Okay? So I need to take the derivative. My goal, big picture, what am I trying to do? I'm trying to minimize A. Where do minimums occur? Critical points or endpoints. So therefore I need to find critical points. Never forget the big picture of what you're trying to do. Now I could do product rule because I'm multiplying two things, but I think I'd rather multiply this out instead to make my life easier and not have to use product rule. So what's x times that? That's just 30. And then what's x times 2? That's 2x. And then what's 4 times that? That's going to be 120 over x. And then the last one, what's 4 times 2? That's 8. That's 8. Did I mess up somewhere? I messed up somewhere. Let me back up. No, I don't think I messed up. I'm good. I'm good. Okay, let's combine like terms. 30 and 8 get me 38. Okay, now I'm going to rewrite this. That's x to negative 1. Now, what are we trying to do? We want the derivative because we're trying to find the max and min of A, which occurs at critical points and endpoints. So let's find critical points. We need the derivative. So derivative 38 is 0. That's 2. The derivative of x negative 1, we bring the negative 1 in front and decrease the power by 1. And now we have the derivative of this. Oh, it's minus 120 over x squared. But we want a common denominator. So I will multiply this by x squared over x squared. And now we have a derivative of 2x squared minus 120 over x squared. So the question is, what are critical points? It's when the derivative is 0. Well, when is this 0? It's when the numerator is 0. So I set the numerator equal to 0, add 120 to both sides, divide both sides by 2, square root both sides. Now, this x is the length of the side, and lengths are not negative, so it's going to be positive radical 60. Now, I'm going to get an approximation for that. I will do that for you guys and gals. About 7.7. That will help us in the future of this problem. Now, that's where derivative is 0. The other critical point where the derivative is undefined. Well, when is this fraction undefined? It's when the denominator equals 0. Well, x is 0. Well, that actually is not a critical point, and I'll tell you why. Critical points cannot be endpoints. And the shortest this side could be is 0. X can be the smallest is 0. That's an endpoint. Therefore, x equals 0 is not a critical point. And this is good news because it appears we have only one critical point. And if that's a relative min, it has to be an absolute min by that theorem that we learned recently. So let's do this. Let's check to see if that's a relative min. And you should know the justification for a relative min is the derivative changes from negative to positive. So we want to check the derivative around that point. Let's plug in 1. I can do this pretty easy. Plug a 1 for x, that's 2 minus 120, that's negative. Over a positive, that's negative. That was easy. Plug in 10. 10 squares 100, that's 200 minus 120, that's positive. Positive. So I'm not going to write all this out, but if this were an actual FRQ, you would say A has a minimum, relative minimum at x equals negative 60 because A prime changed from negative to positive. Then you would say, since A is continuous and x equals negative 60 is the only relative extrema, therefore it's also the absolute extrema. So we have an absolute minimum at x equals radical 60. So what are they asking for? The dimensions of the garden. So we actually aren't done. We found x, we found this distance. We'd have to find y, but that's easy. Y is just 30 divided by x. So our y would be 30 over radical 60, right? Our x is radical 60, but we're still not done because we want the dimensions of the garden. So this bottom would be our x plus 4, and the side would be our y plus 2. So we'd have to add 2 to that and 4 to that, and that would be our answer for that problem. So that is that.